Alright, in this video I'm going to be talking about what happens when you're titrating a weak base. I'm using pyridine as my weak base with strong acid, hydrochloric acid, and what is the pH when you are at the equivalence point. In my opinion, this is the trickiest kind of calculation that you have to do, and you'll see why as we go through the video. So first, I just want to say this is what pyridine looks like. Pyridine is an organic base. At every vertex here is a carbon atom, and every carbon atom has enough hydrogens to fulfill its octet. So this is just a shorthand way of drawing what pyridine is, but I'm going to just abbreviate it generically as R3N during the course of the video. So this is what our pyridine is. So first, let's talk about what happens at the equivalence point. The equivalence point is the point at which your base, pyridine, and your acid, hydrochloric acid, have the same number of moles. So let's determine how many moles, how many milliliters of the hydrochloric acid we need so that we have exactly the same number of moles of hydrochloric acid as we do of pyridine. So let's first figure out how many moles of pyridine we have. We have 20 milliliters of pyridine. There's 1,000 milliliters in a liter. And the molarity tells us that for every 1 liter, you have 0.25 moles. So that means we have 0.005 moles of pyridine. Again, because we're at the equivalence point, that means that we have to have the same number of moles of hydrochloric acid. Let's determine how many milliliters that is. So we know that we need to have 0.005 moles of hydrochloric acid because we're at the equivalence point. Our molarity tells us that there's 0.1 moles in every liter of the HCl solution, and every 1 liter contains 1,000 milliliters. So that means in order to reach this equivalence point, we need 50 milliliters of the HCl solution. We will need that information in a little bit. All right. Now, when you're talking about adding a strong acid or a strong base, whenever you have anything strong and you're adding it to something that's weak, it is going to be a reaction. Reactions need Icy Final Tables, not ICE tables. So we're going to talk about an Icy Final Table, and Icy Final Tables are in terms of moles. So let's predict the products of this reaction. We have weak base pyridine, R3N, reacting with strong acid, HCl, and the products of this reaction. R3N is a base. The base is going to pull the proton off of the acid. So after the base pulls off the proton, you form its conjugate, R3NH+. And after HCl donates its proton away, you're left with chloride, Cl-. Now we're ready to set up our Icy Final Table. So our initial number of moles of the base is 0.005. And because we're at the equivalence point, like I said, our number of moles of our acid are the same. We have no moles of conjugate acid, R3NH+. And we have no chloride, but honestly, I don't really care what's going on with the chloride. Chloride is an ion that does not affect the pH. It doesn't participate in the reaction. So I'm not going to worry about its initial concentration or what happens to it. So I'm just going to ignore chloride throughout. Now, the change for an Icy Final Table, you're looking at the stoichiometry of the reaction. Which one of these reagents is in excess? Which one is limiting? At the equivalence point, you're at this perfect place where they are both absolutely equal to each other. So during the course of the reaction, all of the pyridine will react with all of the HCl. We will gain that same amount of conjugate acid, R3NH. So, final, after the reaction has occurred, we have no pyridine, we have no HCl, we do have 0.005 moles of conjugate acid, R3NH, pyridinium. And again, we don't care about chloride. Let's talk about its final molarity. Remember that molarity is moles per liter. So here we have our number of moles. So how many liters of solvent do we have? Well, we took 20 milliliters of the original base and we added 50 milliliters of the HCl. So that means we have in total 70 milliliters of the solution, which is 0.07 liters. So to get the final molarity, 0.005 divided by 0.07, giving us a final molarity of 0.0714. Now, we have to analyze this in order to tell what is our pH even going to be. Is it going to be an acid, a base, or is this a buffer? Well, the answer to that is that this is an acid. Look at this. We have R3NH. That's really the only thing that we have in solution that's going to change pH at all. And it is an acid. We know it's an acid because it has a proton that it can donate away. It is also an acid because it is the conjugate of the base. The base is pyridine, R3N. When you add a proton to it, it becomes its conjugate acid. So this solution is going to be acidic. This is where it gets tricky though. We need to put this into water now and solve an ice table in order to determine what is occurring in this solution. So let's take that conjugate acid, R3NH, and put it into water to determine the pH. So we have acid R3NH plus, and it's going to be reacting with water. We have nothing strong in this, so this is an equilibrium. Water is going to act as the base, pulling the proton off of the acid. After it pulls off that proton, you form hydronium. After the conjugate acid here gives its proton away, you're going to be left with R3N. Because we're at equilibrium, we care about an ICE table. So the initial concentration of this acid is 0.0714. We don't care about water. It doesn't participate in the reaction. It doesn't appear in any Ka or Kb expressions. So it doesn't change the pH. So we don't really care about water. We have no hydronium. We have no R3N. The equilibrium is going to shift to the right because we have no products, and we have to have some products at equilibrium. So the change here is going to be minus x. It's minus 1x because our coefficient is 1, plus x, also because those coefficients are 1. So at equilibrium, the concentration of this is 0.0714 minus x. Concentration of hydronium is x. Concentration of pyridine is also x. This is going to be plugged into a Ka expression. Remember, this is an acid. We have produced hydronium, so it will go into a Ka expression. So the Ka expression in terms of concentrations is going to be the concentration of hydronium to the first power, because its coefficient is 1, times the concentration of pyridine, R3N, also to the first power, because its coefficient is 1, divided by the concentration of R3NH, plus. Also to the coefficient, to the power of 1, because its coefficient is 1. Water is already included in the acid dissociation constant. All right, we're very close to plugging things in. We need a value for Ka. We don't quite have it, but we can calculate it. So I zoom back up here to show you that we have a Kb. We know what the Kb is for pyridine. Remember, this is an easy one to forget, but it's super important. Kw is equal to Ka times Kb for conjugate pairs. So since we know the Kb for pyridine, we can calculate the conjugate's Ka. So that's going to be 1 times 10 to the minus 14th equals the Ka times 1.7 times 10 to the minus 9th. That gives us the Ka for this acid of 5.88 times 10 to the minus 6th. Now we are ready to plug things into this Ka expression. So 5.88 times 10 to the minus 6th is equal to x squared, x times x, divided by 0.0714. Remember, we're making an assumption here. We're assuming that the equilibrium is not going to go very far to the right. So at equilibrium, we can say that this is going to be roughly the same. We're neglecting the change in x. So then, solving for x, x is equal to 6.48 times 10 to the minus 4th. Whenever you make the assumption that you neglect the change in x, it's good practice to check your assumption. You check your assumption by putting x divided by the initial concentration times 100. That gives us 0.9%. If your change in x is less than 5% of your initial concentration, then your assumption is valid. So here we are only 0.9%, so our assumption is perfectly valid. So now, let's take a step and analyze what we have. We know that this x is equal to the concentration of hydronium. Whenever you know the concentration of hydronium, you can determine the pH directly. So our concentration for this of hydronium is equal to 6.48 times 10 to the minus 4th. The pH is equal to the negative log of that concentration of hydronium. So the pH of this solution is equal to 3.19.